So case 1, or excuse me, case 2. So since f is continuous on AB, so what is this? We've got a continuous function on a closed bounded interval, right? So what did we say about that last time? So if you're continuous on a closed bounded interval, then you have to achieve your global maximum and minimum. Yeah. Okay? So f is continuous on a closed bounded interval. That was one of our conditions, right? So we said it had to be continuous on a closed bounded interval. Okay? F achieves both its max and min. So part A, I guess, of case 2 is to say, well, since it's not a constant, either it increases at some point or it decreases at some point because it's non-constant. Okay? Since f is non-constant, assume there's an x naught, I guess, contained in AB, so that f of x naught is greater than f of a. So we've broken it up into two cases. One is where we're constant, and clearly if it's constant, the derivative is going to be 0. The second case is, okay, we're going to assume that it's not constant. Well, we know it has to have a global maximum and a global minimum, right? And if we say that since it's not constant, in one case we're going to assume that there's at least one value where it rises above f of a, meaning above f of b, then it has to have a global maximum that's not where? Then it has to have a global maximum that's not at the endpoints. Okay? Not, that's the key, at the endpoints. So right now we've said that it has to have a global maximum, and that global maximum cannot occur at the endpoints. Okay? So it's also a what? If it's a global maximum and it's not at the endpoints, then it must also be a what?
Local max.
It has to be a local max, right? Since we've got a local max, where the function is differentiable, that derivative exists everywhere. What did Fermat's theorem say?
That local max,
You on track?
yeah, it differentiates and it's 0.
Well, so if we have a local max or min at some point, and the derivative exists, which we said it did because we said it had to be differentiable, then that derivative must be 0. So by Fermat's, learned over the weekend. F prime of, so it must have a global maximum, let me just add to that, a global max at x equals c, at x equals c. Therefore f prime of c must equal 0. B, you assume that there's an x naught contained in the interval, so that f of x naught is less than f of a. So it's also less than f of b. So because of that, you have to have a global minimum, and it can't be at the endpoints because we said it had to be below. There is at least one point that's below those y values, and so then you get a similar result.
What's the last word?
Similar. So then at that point, you have to have a global, instead of, so you just repeat what we said up here, but instead of saying f has a global maximum, you say f has a global minimum that's on the interior. So here was the issue, right? We knew as soon as I said that f was continuous, on a closed bounded interval, we knew that it had to achieve its global maxes and mins. But what could have happened? Those could have happened at the endpoints. Okay. So then we broke it up into cases. We first examined the constant case. Then we said since it's non-constant, at some point it has to rise. If it's risen, then the global max can't be at the endpoints. The global max would have to be on the interior. Well, if it's on the interior, then it's also a local max. That added with the condition that it must be differentiable allows us to invoke Fermat's theorem, which then says we've got a place where we've got a horizontal tangent line.